Hi, this is Mingyao from Singularity Engineering. This is the third in my video series on ventilation studies. In the first two videos, we've covered how to take a model from Rivet and prepare it for analysis in Ansys CFD. In the second video, we did a quick analysis and looked at how to calculate the age of air using an additional variable, and that allows us to look at how long air circulates around inside a particular room. And in this video, we're going to take a closer look at detailed modeling, specifically how to model diffusers. Now, diffusers are very commonly used in HVAC applications, but obviously the challenge of simulating them is that they're not just straight inlets or outlets. They direct the flow in specific ways. And typically, the way they're specified is as follows. As you can see, we have here a metal air diffuser. The performance of diffusers are listed with a CFM number and then a throw number. The throw number indicates how the distance at which the diffuser can throw an air at 150 feet per minute, 100 feet per minute, and 50 feet per minute. So these are typically what we get when we try to model a diffuser. And the goal in simulation is not to model the detailed diffuser, but to come up with an appropriate model. So the way I'm going to go through the process of what I would do to model one of these diffusers. We're going to start with the geometry, and we're going to do a CFD analysis on it. And I'll talk about this geometry a little bit once we start the meshing process. Okay, so this is our simulation of the diffuser. Let's see, it's a 1/8 sector of a standard ASHRAE room. We're modeling a square diffuser here, so this will be our diffuser. These are the symmetry planes, and then I have an outlet specified on the bottom here. And the goal is to try to figure out the performance of the diffuser as a function of the throw distance, so we can come up with a good model for it. So let's go ahead and set up this simulation here. I'm going to use virtual topology to merge this area together to simplify this model. That'll be our inlet. We have symmetry planes on either side. So let's go ahead and run the simulation, set up this model. So we're gonna set the size of this to about 1/2 foot in size, we want the diffuser area to be well defined, so maybe 1/10 foot, maybe even less than that. So that circle around my cursor shows me kind of roughly how fine the mesh will be in that area. We want to have inflation on all the walls. So there aren't too many walls in this model, but these are the walls. And typically what I do is I use first layer thickness. I use the first layer, first aspect ratio of 10, and we'll have 10 layers of boundary layers. So let's go ahead and set up a mesh and get the simulation going. You can see the mesh finished really fast. Here we have our area. That'll be where the inlet is, and let's go ahead and proceed with the analysis. Okay, this is our model here. This is our inlet. We have an outlet. We have some walls. So I'm going to let's first put in the symmetry boundary conditions. This is a 1/8 symmetric model, so these are the symmetry boundary conditions. We have an outlet back here. Oh, I should specify that there's 0 psi pressure here, and then we have an inlet up here. So for the inlet, we're going to define a mass flow rate. we're going to use the expression like we did before. So I'm actually going to start with the CFM expression. So for CFM, let's start with the low side. So we have a diffuser that produces 80 cubic feet per minute of flow. And then we're going to put an expression for convert that to a mass flow rate. Okay, so the mass flow rate will be the CFM times the density of air, which is 1.185 kilogram per meter cube. And because we're only using 1/8 sector, we need to divide this by 8. Okay, so if we calculate this, right, it shows me this is the mass flow rate over here. We also want to specify an angle. And this will be the angle of the flow according to, so 0 would be, we'll have it come straight down, and kind of 90 would be going horizontal along the top of the ceiling. So here we're going to do 60 degree angle. Okay, so those are kind of our input values. Now we can define our inlet. Okay, so we're going to do a mass flow rate, and we're going to use our expression of mass flow rate. The direction is going to be according to a cylindrical coordinate system. The global coordinate system was defined such that the center here, the axis definition will be the y-axis. So I just need to put in the coordinate system, the flow direction as a function of that in axial and radial direction. So there'll be no change in the theta direction. Axial direction will be minus cos angle, and the radial direction will be sine angle. Okay. So this will create a flow that will come out at 60 degrees. So if we see 45 degrees as kind of directly diagonal, 60 degrees is a little bit more towards the wall. And that's the kind of oftentimes the way diffusers work. They shoot the air along the wall, have the jet go around the wall, and then cause circulation inside of the room. What we want to do is we want to run through a series of CFMs and angles. If we look at the data sheet we have here, you can see that at different CFMs, there are different amount of throw. So for a particular type of diffuser, we can mock up the performance of that by running that diffuser at different CFMs, varying the angle, and trying to match up the amount of throw that results in this. So we're going to go ahead and make these into parameters. So use these as input parameters. And if we go back to the Workbench project page now, you can see we have a parameter set. Once we run the simulation, look at the results, we can have some output parameters. That's going to take a while. So I've prepared an existing model that's done all of this already. So let's take a look at a result, and I'll show you how I've set up those parameters. So a quick switch of data shows you what I've done here. If I turn on the symmetry, and I want to turn off the mesh, you can see the jet here coming out of the nozzle. I can even turn on the vectors to show you which direction that is pointing. So let's go find the inlet. And we can see that the way the flow is pointing is in like a 60-degree angle. So when the flow comes out at a 60-degree angle, I'm not sure why there's one little stream that's going off in some strange direction. I guess it's 0, so we don't really know. which way it should be pointing. So it's kind of an indeterminate point at that location. But the rest of it is going in the same angle, and you can see the stream of the flow coming out of it. The interesting thing with the HVAC industry is that they measure flow speed by in feet per minute, and obviously normally we do velocities in per second, so we just multiply this by 60, and that's our feet per minute value. So this is about 180 feet per minute at the max here. What I then did was that I created a series of these planes. I did it at every once every 2 feet, but you can certainly do it more closely, maybe once every foot. And I can plot the velocities on each one of these planes. So maybe let's color this one using velocity as well, so we can kind of see where the jet goes. Another interesting thing that we can do is we can plot the ISO surfaces for 150, 150 feet per minute. So let's do ISO surface 1, and for this one we'll set the velocity, and it'll be, let's see, so 50, I think, well, we want to start with 150. So 2.5. Okay. So you can see that that's the extent of the 150 feet per minute region. Then we can do another one here. And I'll do velocity. So this will be 100 feet per minute. So this will be 1.6. Let's do that. So that's the shape of the plume that's in 100 feet per minute. And finally, we can look at 50 feet per minute. Uh, 0.83. Okay, so this is kind of, if you're familiar with HVAC flow profiles, this should look pretty familiar in terms of the shape of the flow. And you can see that the longest throw distance is kind of along this plane. This is a 1/8 symmetric model, so we'd expect that kind of 4 of these kind of jets coming out. But this is just qualitative. We can kind of get a feel for what this looks like. The next step is we want to create a series of expressions. So I can actually right click here and say edit this in command editor, and then just modify all of the expressions. So basically I've created expressions at each of the plane locations to calculate the maximum velocity. I multiply by this by 60 seconds, so we get feet per minute values, or just feet values. And then I made them all parameters. So just right click on each one of these options, make these into output parameters. Then I can do a design of experiment analysis. And here you can see that I've specified for each of the input parameters, in this case just the angle and the CFM, I've set some limits. So the angle I want to range between 35 degrees and 75 degrees. So it's a fairly large sweep in the angle. On the CFM side, I'm varying between 1.33, which is 80 CFM, up to 12, which is 720 CFM. So, and I'm just using a standard design of experiment setup here. So the design of experiment is central composite. So it did 9 simulations, tried to figure out and interpolate between all of this data. But here we can go to, we can take that one step further. So now that I've had a basic response surface generated, in Ansys we can do verification points. So in addition to the 9 initial points, I've told Ansys to gather another 50 points that it selects to try to fill out the changes inside of this region I'm interested in. So between 35 and 75 degree angle, between about 80 to 720 cubic feet per minute flow rate. And you can see that it's gathered the feet per minute velocity data for all of those. Now I have about 60 points of data. From that data, Ansys is able to create an interpolation function using a variety of methods. I'm using a genetic aggregation, so it's using 4 or 5 different interpolation methods, trying to interpolate between all of those data and coming up with a curve that looks like this. We can look at the fitting is good because I fit the data to that. And I've put the verification points into refinement points to kind of update my response surface. So I should probably do some more verification points, see how that matches up with the predicted data, but this is probably sufficient for our purposes. So then the next step here is that we're going to do a optimization study. So let's go back and find our material list here. So here, for example, we have this 80. So this one. So let's do 120 feet per minute. go back to this step and do it. So let's try doing it in here. So we're going to change our seek target. So we want to seek a target at 2 feet per second, and we want, what was the numbers? 4, 6, and 8. Let's seek a target at 50. Okay. You can see the optimization method is screening, which means that we're going to scatter 5,000 potential designs around our design domain, and we're going to try to pick the ones that's most similar to the ones that we've selected before. We want to figure out an angle that best fits these are objectives and criteria as constraints. Okay, so it's found 3 designs here for me. So angle 74, 70, and 65, or 66. You can see the flow rate is all about the same, but there's a bit of difference between the throw, right? The data shows throw should be around 50 at 8 feet, around 100 at 6 feet, and at around 150 at 4 feet. So I would say based on this data, maybe like 74 seems to be the closest one. We're not going to get it exactly. There's obviously a lot of variations in testing and the way the jets are actually formed inside of the diffuser, but we certainly want the 8 feet number to be similar, and this looks pretty good. We can take a look at the candidate points here to see what how they differ from what we had earlier. We can also take a look at the trade-offs. So we're looking at the variations between different locations and how fast the flow is moving. Sensitivities is interesting. You can see that at near the inlet, right, the angle is very much has a huge impact on the first couple of 2, 4, 5, 6. No, I say 2, 4, 6, and 8 feet. We have a pretty strong influence. But as we get further away from the diffuser, the actual CFM becomes dominant, and the actual angle becomes less and less relevant. So this gives you some interesting ideas about, if you need to match up the flow in the near field, what you would have to do. And this shows you that when the flow speed picks up, let's say over here, then the angle doesn't really matter, and we can be pretty confident about picking the right, getting better correlations with the data. But near the inlet, the angle is really important for this. There's another option is that we can look at the sample plot, which lists all 5,000 potential designs. So for example, the second column is we want this to be around 2 feet per second, 2 cubic feet per second. So I'm going to filter out all the, oh, this is way too high. We want to be down here somewhere. So we don't want any of this. It's a little bit slow initially because of the large number of points, but we just gotta drag this down. Alright, so we're at 3. I need to pull this down a little bit further to about 2. Right, and then you can see we have a lot of values here in terms of where if I sweep through it, it shows me that in this range, I can look at different angles, and I can look at dynamically how these values change. Looks like we should have been on the higher end of the angles, so maybe somewhere around there, and now we have pretty steady performance across all of these. Some of these are a little bit more, changes a little bit more than others, but we're trying to match up our 4, 6, and 8 feet values here, and you can kind of manually pick one, or you can use this optimization method to pick one. So What this allows us to do in the end is we can, if we know the CFM we want inside of a room, and we know the type of diffuser we want, we can go and I can read the spec sheet and go to this table and find the right angle that will approximate the flow of the diffuser. So we'll do that in our next example, where we're going to take our diffuser here. Let's just say we have I don't remember what CFM I wanted in that room, but we can take an example of one of these ducts with the right CFM and put this diffuser into the room and see how it interacts. And obviously in a room you have multiple diffusers, so we can look at how all the diffusers for the supply, and then put in some returns and see how all of those interact with each other. Hopefully you enjoyed this presentation. We want to do a few more videos, so keep an eye out for more simulations videos on ventilation studies using Ansys CFD. Thank you for your attention, and please subscribe to our channel. Have a good day.